All right. Hello, applied math students. Today we are starting Chapter 1, Section 1, Review of Sets and Set Operations. All right. Now, basically, what I need you to think about as a set is a collection whose members are specified by a list or rule. So, for example, my 6th period class, which is you guys, is a set. And each one of you is a part of that set, or what we'll call later an element of that set. So a set is a collection of numbers, a collection of people, a collection of something. Okay, so you guys in 6th period are a set. If I wanted to say my students in 7th period are a set, I can do that too. That's a separate set. Okay, I can have a set of students for my 6th period. I can have a separate different set of students for my 7th period. All right? So that's kind of what a set is. In the list, when you list out a set, you only have to label each element once. So let's say you have a set of numbers, and there would be no reason to write 2 twice in it. Even if you see the number 2 appear twice, you really only need to list it once in the set. So you don't have to have it duplicated. You can just keep it once each. So here's an example of a set. Set S, so this is the name of the set here, the name of the set. And the set includes Alabama, Alaska, Arizona, and Arkansas. So this is a set of all the states whose name starts with A. Okay, again, it's just a collection. It's a collection of all the states' name starting with A. A couple things to keep in mind, especially with notation. The name of a set is always a capital letter. So name, always capital letter. And another thing to keep in mind is we use these little squiggly brackets here, this one on the left side and the right side, as a way of identifying a set. Okay? We don't use parentheses, we don't use square brackets, we use these squiggly brackets. So these squiggly brackets are important, please keep them in mind. Whenever you write a set, you're going to have to use those little brackets to indicate that that's the set. All right, let's erase what's there. Set S is a set of states starting with the letter A, as we mentioned. Okay, when a rule is used to specify a set, you'll see written as this. So here's again more notation to be aware of. Notice the same thing, a capital S, indicating the name of the set. And you got your squiggly brackets. Everything inside the squiggly bracket is what the set is contained of. But if you write it as a rule, and you'll see what I mean by rule in a minute, but you'll write it as, there's a little X, which means X represents an element. And you've got the little colon here to say that it's an element of these conditions. So the way we read this is S is a set of all X such that. So to kind of abbreviate that, we have S, which is this guy, is a set, thus it equals with the brackets, of all X, which is this guy, such that. So this colon here is kind of the phrase such that. And then what comes after the colon are the conditions that we meet with that. So it could be, and we'll look at an example here. Here's an example down there. The finite sets, I'll talk about finite sets in a minute, but just to give you an idea of how to read that. Here's a set Y, which contains all elements Y, such that, and then this is the condition, Y is all even whole numbers less than 10. So another way you could have written that set would be, you could say that Y, a capital Y, and I know all my capitals, and I just make lowercase capital Y. Lowercase y is just small y's. So imagine it's capital. All right, this set is the same as this one. Let's see, it says all even whole numbers less than 10. So 2, 4, 6, 8. That's the same thing. So you can write the set like this, or you can write it like this. Doesn't matter. However, you'll see this referenced a lot because sometimes sets are so big that this would be the simpler way of writing it rather than all the elements. It just happens in this case there weren't that many elements, so it's probably easier to write it like this, but that's not always the case. All right, so go back a second. Nothing can partially be in a set. So there's either something in a set or there's something not, or it's not in the set. So for instance, you guys are in my 6th period. You are not going to be in my 7th period, okay? You're not going to be in those two places at once. I guess technically it is possible, but not in the set world. Like for instance, a set of even numbers, 2, right? 2 is either in that set or it is not in that set. So a set of even numbers, 2 is in that set. It's not partially in, it's not any, it's in. The number 3 is not in that set because 3 is not an even number, okay? So it's either in the set or it's not. There's no halfsies. A finite set, it's pretty simple. It contains a finite number of elements, so a specific number of elements that you can count up to. An infinite set has an infinite number of elements, meaning there's an infinite number of elements. I mean, they're just, you can't count them all, they're just infinite. I don't know how else to say that. Oh, but just to go back, I guess, and read that. This says the set Z contains elements Z such that Z is all odd whole numbers. See, that would be an infinite set because there's an infinite number of odd numbers. That list would go on forever. So elements. Here's a different set we're calling I. So the set I of even positive integers less than 15 can be written a couple different ways. You can write it like this. The set I, all right, contains element n such that n is even positive integer less than 15. Or, like I said, you can kind of write that out. I equals, and then you can write out what all of that is, an even positive integer less than 15. So 2, 4, 6, 8, 10, 12, 14. That's the set. Okay? So remember, all set names are capitalized, all elements in sets, if variables are lowercase. So to indicate X is an element, which means when I say is an element, it's a member of that set. So for instance, 2 is a member of set I. We write it like this. X is an element of X. So this is the element right here that's inside the set. This is the symbol indicating element. And then this is the set name. So this is the element, the actual element or member. This is just a sign to indicate that it's actually an element. And then this is the name of the set. Okay. When X is not an element of a set, then we write this. So notice it's just it's that element sign, that E symbol, but with a slash through it. Okay. So like I said before, an example, just to get your head in the game of this, 2 is an element of I. As you can see, 2 is a member of that set that we call I. All right, an example of one that's not a set. Well, 3 is not a member of that set, so we can say that 3 is not an element of I, because 3 is not a member of that set. So that's just the way we would write it. All right, again, lowercase letters indicate the element. That's why these are lowercase. Those are indicating some of the elements. That can be the 2, 4, 6, 8, 10, 12, or 14 in this case. And the uppercase letter will always represent the actual set, the name of the set. So the syntax is very important. Subsets. A set A is a subset of B written like this. It's got like a little, it's not like a C, it's kind of like a sideways boomerang. I don't know, something along those lines. But it's written like this. A is a subset of B, that's what that says, if every element in A is also in B. So for example, let's take your class, 6th period. Let's say I split that set up. Let's say I made a set of guys and a set of girls. and we'll call guys set A, okay? And we'll call the whole class set S for students, right? If that's the case, if A is, all the guys are in the guy set, but all the guys are also in my class. So that group is a subset of the class. It's a group inside a group, if you want to prefer it like that, okay? So if A is a subset of B, so that means A, all the elements in A are also in B. Like I said, all the guys are also in my class. And B is also a subset of A, which doesn't really apply to my example, but let's just say that every element in B was also in A. If both of those are true, then that means B and A have exactly the same elements, in which case we say A equals B. So an example of that, let's say I called A the set 1, 2, 3, 4, and I called B the set 1, 2, 3, 4. Right? A is a subset of B because every single member in A is also in B. But of course, as you can probably tell, B is a subset of A because every element in B is also in A. So if both of these are true, we say that A is equal to B, that they are the same set. So only under those conditions. That doesn't happen a lot, but I'm just saying if they're vice versa subsets, then that's defining them as equal. All right, so let's look at an example. So here's what I determined set A. Set A is the elements 2, 4, 8, 12. Set B is the elements 2, 6, 10, 12, 14. And set I is 2, 4, 6, 8, 10, 12, 14. Now, since all elements in A are also in I, notice all the elements in A, 2, 4, 8, and 12. All of those elements are also in I, 2, 4, 8, and 12. That means A is a subset of I. All the elements in A are also contained in I. Since all elements in B are also in I, B is a subset of I. So notice B, the elements are 2, which is also in I, 6, also in I, 10, also in I, 12, and 14 are also in I. So every element in B is also in I, so B is a subset of I. It's a smaller group within another group, basically. Now, is A a subset of B? Is every element in A also in B? Well, I have 2 in both. I have 4. Is every element in A also in B? 4 is not in B. So A is not a subset of B. So we could write it like A is not a subset of B. All right. It is not a subset. Is B a subset of A? Is every element in B also in A? Well, for example, the 6 is in B, but the 6 is not in A. So that is not true as well. So both of these are not true. Or no. All right, and the last thing I'll talk about for today in this video is unions. A union is a combination of all elements of 2 sets. So let's kind of look at an example. Well, okay, so let A and B be sets. This is just a definition of a union. The set A union B, which is how it's written, so kind of like subset sign, but like this, like the use, it's kind of turned a little bit. It's now a U. That indicates union. You're taking A and B and you're bringing them together. This is called the union of A and B. It consists of all elements which are in A or B or both. And the fancy way to write it is like this. So again, this says that the set A union with set B, which is bringing the 2 sets together, is by definition all elements of X such that X is an element of A. So we're talking about our set being X is an element of A or X is an element of B. So let's look at an example. So let's call A the set 2, 4, 8, and 12, and B the set 2, 6, 10, 12, and 14. Right? Kind of the same as what we were looking at before. A union B, which means if I were to combine these sets, I'll have every element of A which will be 2, 4, 8, and 12. And, and every element of B, which is 2, which I already wrote, so I don't have to write it again, 6, 10, 12, which I already have, so I don't write it again, and 14. So this is the union of A and B. It's every element in A, every element in B being brought together in the same set. Now, typically these should be written in numerical order. I didn't write it in numerical order at first because I just wanted to say all of A and then the rest of B. But formally, you should have them, all those values written numerical order, like that. Okay. Now again, even though 2 and 12, which is not here, but 2 and 12 are in both sets, we don't have to list it twice. We only need to write it once. There's no reason for having that duplicate value. Okay. All right, I'm going to cut it off there. Just keep the video simple. We'll pick up with intersections in the next one. Let me know if you guys are stuck on anything. Come see me during class or after class or any of that. Okay. Or message me under Minds. Till next time, guys. I will see you later. Bye-bye.